Okay, it's the video for measures of center and variability. First thing you notice, I am starting off with the lesson page because the very first lesson page is going to be your best friend while you go ahead and do this particular topic. It gives you all the definitions you need, and you can refer back to this page while you're doing the topic's questions. So open up the lesson page and have this open in the background. Let's go through these definitions real quick. Measure of center. A measure of center for a numerical data set summarizes all of its values with a single number. So a measure of center helps you kind of find like the middle of the set of values. It gives you one number that kind of represents all of the data, and that number is somewhere in the middle. Then you have measure of variability. A measure of variation for a numerical data set describes how its values vary with a single number. So it's not trying to describe all the values with a number, but it's supposed to describe how the values change or vary. That's why it's called a measure of variability. So some common number terms, you should know these already. Mean and median. What's the mean? The mean is also called the average. The mean is the sum of all the values in a data set divided by the number of data values. The mean is what you get when you add all the numbers together and divide by how many numbers you had. It is also called the average, and the mean is a measure of center. So when you're talking about what kind of measure they are, a mean is a measure of center. It's like a number that represents kind of the middle of all your data. Median. For an ordered data set with an odd number of values, the median is the middle value. And for an ordered data set with an even number of values, the median is the average of the two middle values. Basically, the median is the very middle number, where half the values in the data set are below that median and half the values in the data set are above that median. So the median is again a measure of center. So I'm going to come back to these other two in a second, but I want to talk about mean and median for a second. And I made a spreadsheet to give you some examples. Let's say you've got a data set. I labeled it set number 1, and it's got 9 numbers in it. And those numbers are 10, 20, 30, 40, 50, 60, 70, 80, and 90. And so the median of this data set is 50, and the mean is 50. Why is the median 50? Because 50 is the very middle number. Notice that there's 4 data values below 50 in this data set, and there's also 4 above it. Well, why is the mean 50? Because if you add all these up and divide by 9, because there's 9 of them, you're going to get 50. Adding these all together makes 450, and 450 divided by 9 is 50. So the mean and the median for this data set, they're both 50. So what's better, mean or median? And that depends. If your data is nice and spread out, and it's nice and spread out real evenly, then the mean is fine. But every once in a while, we get a data set where there are some extreme values, and that makes the median a better measurement. Let me show you. Let's pretend that all of these are car prices in thousands. So 10 is $10,000, 20 is $20,000, 30 is $30,000, etc. If you had these 9 cars and you wanted to know what's like a good value for one of the cars, what's like a normal value for that data set? Well, 50 would be fine, but 50 is the median or the mean. 50 is kind of like a middle number. Half the cars are more expensive than 50, half the cars are less expensive than 50. But what if one of these cars was an extreme example, like a really super nice Lamborghini or something? What if this 90 wasn't $90,000? What if it was 900 for $900,000? Watch what happens now to the mean and the median. Well, the median doesn't change. Of course not, because the middle number is still 50. But what happened to the mean? Now the mean is 140. If we add all of these numbers together and divide by 9, we're going to get 140. So if I were to tell you that an average price of a car for this data set is 140,000, does that seem fair? I mean, 140, that's bigger than 8 of these numbers. It's only less than 1 of them. So the mean here can get thrown off if you have an extreme value in your data set. This happens when you talk about prices of things like cars or houses, where the lower numbers of the values are kind of grouped together because you can't go below 0 and you can't go too low. But the higher numbers can be really, really expensive. Salaries and things like that. Median is a much better use, a better number, a better data is a better term to use and a better calculation to use because it gives you a better idea of what all the numbers are. So let's put that back at 90. Now, what's the difference between the measure of center and a measure of variability? Well, I'm going to give you another data set here, and I'm going to start with 46 and 47. And these are the numbers I'm going to put in. I'm going to go from 46 all the way to 54. And you notice I've got this already to calculate for me what the mean and median are, and it did it. And guess what? The mean and the median for this data set are also both 50. So the mean and the median for set 1 and set 2 are both 50. But look at set number 1 and look at set number 2. Do they look the same? No, there's some very clear differences in there, aren't there? Set number 1 starts at 10 and ends at 90. Set number 2 starts at 46 and ends at 54. But if we just look at the mean or the median, they look like they might be the exact same type of data. So what do we do here? Well, what we want to do is we want to find some other measure that shows us how these two data sets are different. And that is what the measure of variability does. A measure of variability tells us how much the data changes. So going from 10 all the way to 90, that's a big range, or it's a much larger range than going just from 46 to 54. So there's a couple different measures of variability. Check it out. The first one is mean absolute deviation. Now, I know that's a weird sounding term, but it's a super easy calculation, so stay with me. For a set of data, the mean absolute deviation is the mean of the differences of the values in the data set from the mean. So the mean absolute deviation is a measure of variability. I'm going to go over what that said again. The mean absolute deviation is the mean of the differences of the values in the data set from the mean. So let's go ahead and look at set number 1. How do we calculate the mean absolute deviation? Well, we know the mean of the whole data set is 50, and the mean absolute deviation is the average of how different all of these numbers are from that mean. So in other words, how far away is the first data point from the mean? 10 is 40 away from the mean. So the first number is 40 away. Say I was going to write that down. And what's the next number? The next number is 20, and 20 is 30 away from 50. So I'm going to go ahead and add 30. So plus 30. And what's the next number? 30. How far away from the mean is that? It's 20. So plus 20. And then the next number, 40, that's 10 away. So plus 10. And then the next number is 50. That's 0 away. So it'd be plus 0. I don't have to write plus 0. How far away is the next number? 60. That's also 10 away. And the next number is 20 away. And the next number is 30 away. And the next number is 40 away. So I'm going to add all those together. I'm going to calculate what that says right there. So I'm going to say equals, because when I have a spreadsheet and I want it to calculate something, that's what I do. And so when I go ahead and I write this in here, I'm going to copy it over here. I will paste what that says. And there we go. I got 200. Now, again, there were 9 values there because we're including the 50. So how far away from, what is the average amount that all of those are away from 50? All we have to do is take 200 and divide by 9 numbers because there's 9. So equals 200 divided by 9. We get our answer, which is 22.2 repeating. Now, the spreadsheet will actually calculate that number for you, and I already did that. It's right here. The mean absolute deviation is 22.2 repeating. So it's how far away all of these are. You take how far away each number is from the mean of the data set, add them all together, divide by how many there are, and that's your mean absolute deviation. It's the average amount that the numbers deviate from the average of the data set. So it's an average that they are away from the average, okay? So if we do the same thing for this one, all of these numbers are a lot closer to the average. 46 is a lot closer to 50 than 10 is. 47 is a lot closer than 20 is. We add all those together, we're going to get a lot different number. And sure enough, that mean absolute deviation is only 2.2 repeating. So if we look at these two data sets, maybe their mean and medians are the same, but their mean absolute deviations are very different. The mean absolute deviation for set number 1 is 10 times the mean absolute deviation for set number 2. So if we're looking at these numbers, we can tell that set number 2 is a lot closer together than set number 1 because the mean absolute deviation is a lot smaller. What is the other measure of variability? It is the interquartile range. The interquartile range is the difference between the upper and lower quartiles. It measures spread. The interquartile range is a measure of variability. So what is the upper and lower quartile? What's the distance between them? The upper and lower quartiles are referred to as the third quartile and the first quartile. And basically they are the middle of the upper half of numbers and the middle of the lower half of numbers. So if we go back over to set number 1, what is the lower half of numbers? If I include the median, then the lower half of numbers is 10, 20, 30, 40, and 50. Well, what's the middle of that? 30 is. 10 and 20 are lower, 40 and 50 are higher. So the middle of the lower half of numbers is 30. So the first quartile is 30. If I include the median, then the upper half of numbers is 50, 60, 70, 80, and 90, in which case 70 is the middle of the upper half. So the third quartile is 70. So for set number 1, the interquartile range is how far from 30 to 70? And the answer is 40, because 30 and 70 are 40 apart. If we do the same thing for set number 2, we get a first quartile of 48, a third quartile of 52, and those are only 4 apart. So again, the interquartile range for set number 2 is a lot smaller. So we can see in set number 2 that they are a lot closer together because the interquartile range is smaller and the mean absolute deviation is also smaller. Just like with the mean and the median, the interquartile range and the mean absolute deviation are more appropriate at different times. If you have extreme numbers in your data sets, use the interquartile range. But if you don't, then the mean absolute deviation is also good. All right, so now let's go ahead and try and do some problems. Number 1, Trey recorded the number of ounces of water he drank each day in the histogram below. So it looks like we got this histogram. We have some at 91 and 100. We've got some down here at 1 and 10. And then we've got 4150, 5160, 6170. Which of the following is the best measure of variability? Well, first things first, mean and median. Do those measure variability? No, they do not. Mean and median are both a measure of center. So right away, you've already eliminated 2 of your possible choices. You have mean absolute deviation and interquartile range next. Which one is better? If you go into your lesson, you'll have some examples here. Here on page 4, you'll find it. Example number 1 asks you which measure of center would be best, and example number 2 asks you which measure of variability would be best. And they have a dot plot. It's not quite a histogram, but you can kind of tell it's like a dot plot. And when you look at their answer, it says, since the data distribution is not symmetric, the interquartile range is the best measure of variability for use of this distribution. So when we look back at our problem, does this look symmetric to you? Does it look symmetric? Now, it doesn't have to be perfectly symmetric, but does it look symmetric? Well, you've got some extreme down there and extreme up there, not quite balanced, but there's some here, some there. Really what you're looking for is general symmetry. So since this is generally symmetrical, we can go ahead and say mean absolute deviation a lot of times, but because there's these extreme examples and there's more over here than there are over there, interquartile range is going to be better. Number 2, the histogram below shows the homework grades for the last assignment for Mr. Smith's class. Using the histogram, determine the best measures of data. So right away, do these look symmetrical? No. As we go to the right, there's way, way, way more. So we want the measures that are not for symmetrical data. So the best measure of center is the median. Again, the median is the best one when it's not symmetrical. And the best measure of variability is the interquartile range. So when they're not symmetrical, these 2 are your best answers. Again, it goes back into the lesson on page 4. Because the data distribution is not symmetric in the box plot, the median is the best. So when they're not symmetric, you're looking for median for measure of center and interquartile range for measure of variability. Number 3, Mrs. Harrison records the number of vacation days employees in her department have used this year. The histogram below shows the recorded data. Which of the following is the best measure of center for the data? Again, does this look nice and symmetrical? No, so use median. Number 4, where is there a striking deviation? What in the world is that? A striking deviation is an extreme point. You can find an example of this on page 3 of your lesson. Where is a striking deviation? Looking at the dot plot, the point that is separated from the majority of the data is the striking deviation. And that point is at 1 on this dot plot in the example. Where is that right here? Where's the point that's separated from the rest of the data? And it's this point way over here on its own, over by 10. So that's the answer there. Number 5, the lifespans of 8 different cats were used to create the box plot shown above. Which of the following is the interquartile range of the set of lifespans? Let's remind ourselves what the interquartile range is. It's the distance from the first quartile to the third quartile. How do we read the first quartile and third quartile in a box plot? The part where the rectangular box begins on the left side, that's the first quartile. So that would be 10. And where the box ends is the third quartile. If you need a little help interpreting the box plot, here's another quick little explanation about how box plot works. The far end is the minimum value in the data set. So the smallest number is 8. So the lifespan, the smallest lifespan they had was 8. On the right side, that's the maximum value. So the largest lifespan they had was 17. Then, like I just said, the box starts at the first quartile and ends at the third quartile. So the first quartile is 10, the third quartile is 15. And the middle line, the line that's kind of in the middle of the box somewhere in the middle, that's the median. So the median was 13 and a half. So half the lifespans were above 13 and a half, half the lifespans were below 13 and a half. The middle value of the lower half was 10, the middle value of the upper half is 15, the highest value is 17, and the lowest value is 8. So what is the interquartile range? How far from the first quartile 10 to the third quartile 15? They're 5 apart, so the interquartile range is 5. Number 6, the dot plot below shows the number of days with different temperatures last month. So we've got a little dot plot there. What is the mean of the data shown? So again, the mean is the average. This is a pain in the butt problem because they just give you dot plots and you need to find the mean. What is the mean? It's when you add everything together and divide by how many there are. So get a calculator out, or you can use the URL bar, and you have to type in all of these values into the calculator, add them all up, and divide by how many of those values there were. So here we go. 68 plus 70 plus 70 plus 74 plus 7. You know what? Let's just stop for a second and look at our choices. What is the mean? 2,430? Is that the average temperature? There's no 2,430 on here. That's ridiculous. That's not the average temperature. That's a temperature that's way higher, like 20 times higher than even the highest thing here, more than 20 times. So that's definitely not going to be it. 81. I mean, maybe that's kind of in the middle of our dot plot, right? Okay, so maybe 81. What's C? 8? That's way too cold. That's freezing. That's nowhere on here. The lowest number we have is 68. How could 8 be the mean? And last, 5.13, where did that come from? That's even colder than 8 degrees. So while you could add up all these numbers and divide by how many there are, if we just use some common sense and look at our choices, the only reasonable answer we have is 81. So we don't have to do all the legwork of getting a calculator out and calculating the mean for all these. We could just say it's 81 because it's the only answer that makes sense. 2,430 is way too hot, and these are way too cold. The only number that's even close to the middle of all this, and mean is a measure of center, so it should be somewhere in the middle. The only one that's even close is 81. Number 7, a measure of blank for a numerical data set describes how its values vary with a single number. That's exactly what the definition for measure of variability says on page 1. A measure of variation for a numerical data set describes how its values vary with a single number. So it's a measure of variability. Variation, variability, kind of synonymous, just same word, different parts of speech. So measure of variation, measure of variability still works. Number 8, the makers of a new app recorded the number of times the app was downloaded each day for the first year the app was available. Select the correct methods they could use to describe the data. So we're going to select more than one, maybe. It says select the correct statements in the table. So whatever's correct, we're going to select more than one. Let's go through these. First one, to describe how the number of daily downloads varies, they could use the median value. Is the median a measure of how something varies? No, it's a measure of center. So the median is not good for measuring how something varies. So I'm not going to select this one. Next, to describe how the number of daily downloads varies, they could use the maximum. That is also no good. Maximum is the highest number in a data set. Why would just using the highest number show you how something changes or varies? That's not good at all. Next one, to summarize the number of daily downloads with a single number, they could use the interquartile range. Also not good because that is just summarizing the number of daily downloads. If you want to do that, you want to use a measure of center, and the interquartile range is a measure of variability. So none of these work. How about the right side? To describe how the number of daily downloads varies, they could use the mean absolute deviation. Yes, the mean absolute deviation is a measure of variability. It shows how data varies. Next one, to summarize the number of daily downloads with a single number, they could use the mean. Yes, if you want to summarize the number of daily downloads with a single number, you use a measure of center, and the mean is a measure of center. The average is a measure of center. Last but not least, to summarize the number of daily downloads with a single number, they could use the minimum. No, the minimum is the smallest number in a data set, so just saying what the smallest number is would not summarize how many downloads they had, so that's silly. So 2 of these 4 statements are correct. Let's keep it going. Number 9. Mr. Dayton, or Datton, I'm not sure what his name is. Mr. Datton gave his class a 20-point quiz. The results of that quiz are shown below. There's a 19, a 15, a 10, 12, etc., etc. On the number line below, select the numbers that represent the first, second, and third quartiles of the quiz scores. So we want the first quartile, the second quartile, which is also called the median, and the third quartile. And the way that we're going to do this is we're going to put these numbers in order from smallest to largest. So we have to rewrite down all these numbers and we have to put them in order. We need an ordered data set. So what is the first number available? I could do this by hand, but I'm not going to do this for very long because it's a silly way to do it. I'm going to use a spreadsheet, and you can too, and I'll show you how to type it in. But what's the smallest number in here? The smallest number is 5, right? So 5 would be the first number. So we're going to write the number 5. And then what's that number's gone. So what's the next number? Looks like 10. Oh, nope, 7. There's a 7 in here. See, you got to be really careful. You don't miss one. 7. And then 10. And then there's another 10. And this is silly. Let's show you how to do it with a spreadsheet. Okay, so all I did so far is I opened up my spreadsheet program and I just typed in all the numbers that it showed. Okay, I typed them in the same order, so I didn't skip any. 19, 15, 10, 12, 27, 18. These are the same numbers that are right here. Let me show you how you can use your spreadsheet to do this. First thing, you want to put them in order. If you click on this column right here in Google Sheets, you can simply sort them into the order you want them to be in. Now, alphabetically, A to Z, if you translate that to numbers, is smallest number to highest number. So when I click sort, it just changed all the numbers in my column and now they're all in order. So now we can really easily find our median, our first quartile, and our third quartile. We have 16 numbers here. So that means 8 numbers are going to be the lower half. So I'm going to go ahead and highlight those just so you can see them. I'll put them in blue, let's say. And the upper half, I'll put those in green. Okay. So we got the lower half of the numbers in blue and the upper half of the numbers in green. So what is the median? The median should be exactly what splits them. See, we had an even number of data points. We had 16. So there is no exact middle number. So we have to choose the average of the 2 middle numbers. So what's the average of 13 and 15? What's exactly between 13 and 15? 14. So our second quartile, or median, is 14. When I go back here, I can click on 14. So now I have to find the first quartile and the third quartile. The first quartile is the middle of the lower half of numbers. So the lower half of numbers, there's 5, 7, 10, 10. That's the lower part of the lower half. So I'll do this in a slightly different blue. And then if I separate these 8 numbers into an upper and lower half, okay, now I can find my first and third quartile. The lower half of numbers goes from 5 to 13. And sometimes people use a calculation that says the first quartile includes the median, even in situations like these. And sometimes they don't. It depends on, that's kind of a debate in math. So in this one, we are not including the median, which is 14, in a calculation of the first quartile. And that's what Study Island wants you to do. So if we go from 10 to 12, what's the exact middle of 10 and 12? That's 11. So we're going to select 11 for the first quartile. And what's the third quartile? Exactly the middle of 18 and 18 is still just 18. So I'm going to click 18. Now, if you are using a spreadsheet, you can write some formulas to get them to tell you the quartiles and the medians yourself. For example, if I say equals median, I can then select all these values. So it's saying median from A1 to A16, and all these values are in cells A1 to A16. And look at that, it tells me it's 14. This quartile thing is a little different. If I say equals quartile, and I wanted to calculate a quartile for A1 through A16, and I say calculate the first quartile, you might notice a problem. It says 11.5 because Google Sheets uses the median, so it's including the number 14 in there. That's what the problem is. So it should be 11 if you're calculating the median of just the lower half of values. Some calculations use the median to find the quartiles, and some don't. Study Island doesn't want you to use that median 14. It just wants you to take a look at the lower half of values, which are 5, 7, 10, 10, 12, 12, 12, 13. And notice that the first quartile would be between 10 and 12, which is 11. Okay, one more. Select the correct box plot. All 4 of the box plots lie on the same scale and contain the same number of data points. Identify the box plot that represents the situation below. So the middle 50% of the data is not evenly distributed about the mean. So that means we don't want the median in there to be exactly in the middle of this box. We want it to be skewed off one side or the other. So that puts this one and this one out of luck. So we can't have this is the answer and we cannot have this is the answer because we notice that the middle of their lines is right in the middle of that box plot. And that means that the middle 50% of the data is evenly distributed about the median. Because remember, that middle line is the median, right? So this one, there's just as much in the middle 50% of the values go from the first quartile to the third quartile. So since the median is right in the middle, that means that the middle 50% of the data is spread about evenly. So again, not this one, not this one. We're looking for something where the middle 50% of the data, which you can find in the box, is not evenly spread out across the middle line, which is the median. Next, the data distribution is not symmetric. We don't want it to be symmetric. We don't want the data to go from lowest to highest and nice symmetric. So this looks good because this little arm is a lot shorter than this arm. And there is an outlier. There's some outliers. These little data points are outliers. So this is our answer for that one. Okay, and that's it. Remember to work hard and let me know if you need any other help.